This is your presenter, Asloob Mudassar, and I am presenting slide number 8 of the course on atomic and molecular physics. Today I shall be covering these topics, that is exotic atoms, their production, their characteristics and their applications. Exotic atoms, I shall abbreviate them as EAS. So exotic atoms, many short-lived atoms can be produced in particle accelerators and can be investigated. The nucleus of an exotic atom contains particles other than protons, and the atomic shell contains particles other than electrons. In antihydrogen atom, the nucleus is made up of antiproton and the shell contains anti-electrons, that is positron. Particles are distinguished from their antiparticles by charge and the magnetic moment. So charge and the magnetic moment are the two quantities by which antiparticles can be distinguished from their counterparts. Bohr's model for the calculation of atomic radii, energy levels, and the transition frequencies is also applicable to the atoms constituted by antiparticles, or we can say that anti-atoms. So Bohr's model can be applied to anti-atoms. Positronium, neonium, and antihydrogen are examples of exotic atoms. Positronium. Positronium is formed when positron with a charge of e to the power with the charge positive with the charge equal to that of the positive electron and the electron with the charge e minus enter a short-lived bound state. That is, the bound state is due to the positron and the electron pair before they annihilate each other. When they annihilate into two gamma quanta. At the time of annihilation, if the particles have zero kinetic energy, each of the gamma quanta has energy equal to m0 c square. And if you plug in the values of m0 and c, you will find that this quantity is equal to m511 kilo electron volt, where m0 is the rest mass of the electron. So this was about the positronium. Lifetime of parapositron with a spin equal to 0. So the lifetime of the parapositron is 1.25 into 10 to the power minus 10 second, and that of the orthopositron with a spin having a spin s is equal to 1, and there is a small probability for the existing of these orthopositron and there is a small probability for the existence of these orthopositron. The lifetime of the positron is 1.4 into 10 to the power minus 7 second. It decays into 3 or more gamma quanta. Positrons are obtained from the radioactive decay of sodium nuclei with a mass number of 22. Positronium are formed when the positrons pass through a gas or impinge on solid surfaces where the positrons can capture an electron. No accelerators are needed. The reduced mass of a positronium, which we represented as μp, is half that of the hydrogen atom, whereas the reduced mass of the hydrogen is represented here by μh. So now let's relate, as we have said that the mass of the positronium, that is reduced mass of the positronium, that is μp, is half that of the hydrogen reduced mass, which is μh. So let's establish this. You know that in the positronium we have the positron and the electron, both have the same masses. So the reduced mass of the positronium represented by mu p is equal to m naught into m naught divided by m naught plus m naught, and that becomes equal to m naught by 2 as given in equation number 8.1. Now let's calculate the reduced mass of the hydrogen atom. Hydrogen atom has one proton and one electron. The mass of one proton is nearly 1836 times the mass of the electron. And then another m naught stands for the mass of the electron. And in the denominator, we have the mass of the proton, which is 1836 times the mass of the electron plus the mass of the electron. So if you calculate this one, you will get that quantity is nearly equal to m naught as shown in equation number 8.2. So here you can easily establish looking at equation number 8.1 and 8.2 that mu p is equal to half that of mu h. So we can say that the reduced mass of the positronium represented by mu p is half that of the reduced mass of the hydrogen represented by mu h, as shown in equation number 8.3. Now let's calculate the orbital radii of the positronium atom. So if we follow equation number 3.4, that is equation number 4 from slide number 3 of this course, you will find, and I am additionally using the subscript P so that I can say that this is the orbital radii of the positronium atom. So on the left hand side, I have Rn with a subscript P is equal to 4 pi epsilon naught times n square h bar square over mu P times Z times E square. And you know that here I have used the mass of the positronium, that is the reduced mass of the positronium in the denominator appears, and the mu p is actually the reduced mass of the positronium. And if we use equation number 8.3 to replace the reduced mass of the positronium by the reduced mass of the hydrogen, you will get this equation. This expression as shown as shown as a third term from the left, which is equal to 2, and with the parenthesis you have 4 pi epsilon naught times n square h bar square in the numerator, and in the denominator we have mu h times z times e square. So you see that the parenthesis contains actually the orbital radius of the electron in the hydrogen atom, and this can be represented on the rightmost side of this equation, which is equal to 2 times the orbital radius of the hydrogen atom. So Rn with a subscript h. So here you can say that the radii of curvature of the positronium atom has a size which is twice that of the radius of curvature of the equivalent hydrogen atom. Okay, next we want to calculate the wavelengths of the in the positronium when the transition is made from a state n to the state n prime. The wavelength of the positronium following equation 3.18, that is equation number 18 from slide number 3, can be written as. In addition, I have used P as a subscript to stand that this calculations is being done for the positronium. So 1 over lambda with a subscript P is equal to nu bar, which is the wave number with the subscript P, is equal to 1 over 4 pi epsilon square times mu P over 4 pi C, and then the other terms are Z square E4 divided by H cube, and then in the parentheses we have 1 over n prime square minus 1 over n square. That is, the transition is being made from the quantum state n to the quantum state n prime. And Z here indicates that it is like hydrogen-like atom. So any atom can be a positronium atom depending upon the value of Z it contains. And here I have used mu p as the reduced mass of the positronium atom, which is represented in the numerator and shown in red. So now I can substitute the value of mu p from equation number 8.3. That is, mu p in terms of mu h can be shown over here in the second step. And you see that I have written 1 over lambda with the subscript p, which is equal to mu bar p, and then I have separated the factor of half on the left hand side and the other terms are shown on the right hand side. So you can identify these terms to be the wave number of the hydrogen atom for the hydrogen atom. So you can write the third step in this calculation as 1 over lambda with a subscript p is equal to nu bar p is equal to half, nu bar h is equal to half, and 1 over lambda h. And you know that nu bar and wavelengths are reciprocal to each other. That's why I have used this information over here. And here in the you can find out. So if you solve this equation for the value of wavelengths, so you can write that lambda p, that is the wavelength emitted by a positronium atom, is equal to twice that of the wavelength emitted by the hydrogen atom. In the same when the transition is made between the same two quantum states, that is between the state quantum state n and the quantum state n prime. So thus we can say that from the previous equation, that is from this equation given in equation number 8.4 and following equation number 8.6, we can say that the orbital radii and the wavelengths of the positronium are twice those of the hydrogen-like atoms. You see here we are studying the exotic atoms in the case of in the chapters of hydrogen atoms, because the calculations of the exotic atoms can be fairly done with the calculations which are done for the hydrogen atoms. The same formulas can also be used to find out the radii of curvature, the wave numbers, the wavelengths, the energy levels, etc. can similarly be studied for the exotic atoms. That's why we are studying the exotic atoms in the chapter of a hydrogen atom for the completeness. So research about the exotic atoms, how they are produced, that is their production, their creation or generation of the exotic atoms, and their applications in the understanding of the properties of these atoms, and their applications in the study of many interrelated research fields are the ongoing research topics in the field of exotic atoms. So our topic is not, these are, you see that these are the advanced topics, and these are not the fundamentals to the atomic physics. So, but I would like to cover something about the exotic atoms so that the student can have an idea what type of research is going on in the field of atomic physics in these days. Types of exotic atoms. Muonic atoms. You see that in the parenthesis I have shown that the charge of the electron is replaced by the negative muon. So if in an atom you replace an electron with a negative muon, then of course such an atom will be called as muonic atom. Muonic atom, a negatively charged muon with charge equal to that of the electron and a mass which is 207 times the mass of the electron, replaces the electron in an atom and form muonic atom. Muonic atoms have been discussed in slide number 4 of this course. If the replacement is done in a hydrogen atom, it is called a muonic hydrogen. Muonic hydrogen are used in measuring the radius of the protons and in the precision tests in the field of quantum electrodynamics. If one of the two helium atoms, electrons, are replaced by muon, the resulting atom is called muonic helium. So it is not required that you change both of the electrons and replace both of the electrons by the negatively charged muon. Only one of the electrons in the helium atom will be replaced by the negatively charged muon, and the resulting atom will be called as muonic helium. Hadronic atoms. In the hadronic atoms, you replace the charge of the electron by the negative hadron. Hadrons are made up of quarks, Hadronic atoms are used where the strong interactions need to be studied. Then we have the pionic atoms. Here the electron is replaced by a negative pion. These atoms are used to study shifts in the energy levels involving strong interactions. Then we have the kaonic atoms, in which the electron is replaced by a negatively charged kaon. Then antiprotonic atoms, in which the electron is replaced by a negative antiproton. So antiprotonic helium atoms are more famous, used in the testing of CPT, that is the charge, parity, and time symmetry. In the study of these three parameters, the antiprotonic helium atoms can be used, and also in the interaction of a matter versus antimatter conditions. Then we have the onium atoms, particles and its antiparticles form such atoms and has numerous applications in the field of quantum electrodynamics. For example, positronium atom, which is made up of a positron and electron, pionium atoms, which is made up of a positive pion and a negative pion, and muonium atoms, which are made of a positive muon and negative muon, are typical examples of the onium atoms. Hypernuclear atoms. Nucleus contains at least one hyperon. For example, a baryon containing strange quarks, in addition to protons and neutrons. So in a nucleus, you have already some protons and neutrons, and if you replace one of such nuclear particles by at least one of the hyperon, then of course the resulting atoms is called hypernuclear atoms. So what are the possible applications of the exotic atoms? So though the applications of the exotic atoms are numerous, but I am just going through briefly the main applications. In the understanding of fundamental physics, exotic atoms can be used in high precision tests of quantum electrodynamics and quantum chromodynamics, especially at low energies. Muonic hydrogen have been used in the study of the radius of protons. In the understanding of antimatter, antihydrogen are created and used to test CPT, that is charge parity and time symmetry. Muonic molecules can bring nuclei close enough to fuse them at room temperature and is named as muon catalyzed fusion. Now some characteristics of the exotic atoms. Exotic atoms have short lifetimes and decays quickly due to the instability of particles they are made of. As heavy particles are involved in the orbits, due to which the orbits are much closer to the nucleus, and so the sizes of the exotic atoms are small in comparison with their neutral counterparts. Being so close to the nuclei, the energy levels in the exotic atoms are strongly influenced by the shape and size of the nucleus. So this was a brief introduction about the exotic atoms, how they are produced, what are their possible applications, and what are their main characteristics. So this is the end of slide number 8 of the course on atomic and molecular physics.